Hello everyone, welcome to the series of lectures on the course Foundations of Mathematics. This is part 2 of the third chapter, Functions, and in this lecture I will talk about graph of a function. So let's see what is a graph of a function. Supposing I have a function f from the set x to the set y, then the graph of this function denoted by g of f is the subset of the Cartesian product of x cross y such that the second coordinate in the ordered pair is nothing but the image of the first one. Alright. The graph of a function f is a subset of x cross y defined by the set of all ordered pairs x comma y such that the second point here is the image of the first one. Or you can say that the first one is the pre-image of the second one. They mean the same. So these are nothing but the points from the Cartesian product x cross y. So what you are doing, you are collecting all the points from the Cartesian product of the form x comma y such that y is equal to f of x. Clear? Now these points y, they are actually from the range of the function. Can you see that? Since y is equal to f of x, what do you mean by range of a function? All the image points of the points from the domain under the function f, right? That's the range. That's what we discussed in the last lecture. So the graph of a function is actually the Cartesian product of the domain and the range of the function. This is the graph of the function. And these points from the range of the function are only coming here as points y. Okay. So points which are not there in the range won't be coming here. Clear? So this is the graph of a function. So if I give you any function now, we can plot its graph. So to plot the graph, what we have to do? We have to mark all the points of the form x comma y on your graph, right? On your x and the y axis. And those points will represent the graph of the function. For example, if I give you the function, let's say, we'll take a simple one, f of x is equal to xc, where f is a function from R to R. Okay, I'll mention that someday. F is a map from R to R, and this is defined for all real numbers x. Then what is the graph of this function? All the points of the form 1 comma x comma y, where y is equal to f of x. But here if you see, this function is nothing, the graph of this function will have points of the form x comma y, where y is equal to f of x. So that will be x comma f of x, because f of x is nothing but x, right? So the y here is nothing but x itself, right? So that is equal to x comma x. So you are actually looking at all the points in R cross R, that is your R2 of the form x comma x, and that's when you get this line here. Not this one, I'm not drawing it properly. Yeah, x equal to y line. So this point is 1 here, and this will be 1. Then the next point will be 2, and this one here will be 2, and so on. Okay, so that's the line x equal to y, a rough sketch of that. Okay, so if I give you any function, then you can draw its graph. Okay, and the graph is nothing but a subset of the Cartesian product of x cross y, that is your domain cross codomain, and to be precise, the graph is nothing but the exact Cartesian product of the domain and the range. Okay, this is of course a subset of y, and that's why your graph is a subset of x cross y, you can say. Okay, so given any function, you can draw its graph. Now the second question is, if I give you any subset of x cross y, the Cartesian product x cross y, then will that represent a function? That is the question. Will that subset be a graph of some function? So if I give you a subset S of x cross y, the question that comes up next is the opposite of this, what we saw here. Does there exist a function f from x to y such that graph of the function is S? This is the question. Okay. Here what we said, if I give you a function, then the graph of that function is nothing but a subset of the Cartesian product x cross y. That works. That's the definition of a graph of a function. Now, if I give you any subset of x cross y, then can you find a function f from x to y such that the graph of that function is S? Okay, so this question we are going to answer now. So before looking at example, I will tell you all something called as vertical line test. So let's see what is vertical line test. This says, supposing S is a subset of R2. Let's say x is equal to y, n is equal to R2. Let's assume that x and y are R2. So if I give you any subset S of R2, then if every vertical line in R2 intersects this subset S at most one point, at most once, then the subset S will represent graph of some function. Okay, so if I have the x R2, that is your R cross R xy plane, that's R and that's R here, x and y respectively. Supposing I give you some subset now, let's say I will pick up the identity function f of x is equal to x. This is the function y is equal to x, right? Now, if you draw any vertical line here, vertical meaning parallel to the y-axis, okay, that line will cut this subset, this line which I have drawn just now, at most once. In fact, it is cutting exactly once if you see, right? No matter which vertical line you draw parallel to the y-axis, it will cut this line y equal to x at most one point. This is called vertical line test. If you are able to do this, then this subset S that you started with, in our case we started with the points of the form x comma y, x comma x, where x is in R2, this set S. So for this set S, the vertical line test holds true, because no matter which vertical line you draw, it will cut the set S. S is this set. It will cut this set at most once. So there will be a function which will represent as a graph of this function. This line will be a graph of some function. Okay. So in such cases, now how do you determine such functions? If you are able to, make out from the vertical line test that there will be a function whose graph will be this set S, that is this line which I have drawn here, then how do you determine that function? That is what we will see. Before that, I will give you all an example of a subset of R2 which does not represent as a graph of any function. Okay, you cannot find any function whose graph will be that set. So let's look at that. Look at this circle. It's a unit circle centered at the origin, that is collection of all points x comma y in R2 such that x square plus y square is equal to 1. Okay, so this is the set S that is given to us. And the question is, does this set S represent a graph of any function? So let me plot that first. Supposing I'll just draw a rough sketch. Supposing these are my x and y axis, which are R, and supposing I have the unit circle, so it will be a more or less here. Yeah, my diagram is not proper. Assume that it's a circle, unit circle, centered at the origin. Okay, so 1 is here, this point is 1, this is -1, and here again it's -1, and that's the origin. Now if you see by the vertical line test, if I draw any vertical line now which is parallel to y-axis, a vertical line, yeah, of course it's parallel to y-axis, then I have to check whether it is touching this set S. S is this set which I have marked now, the unit circle. We have to check whether every vertical line touches this graph at most one point, right? Now if I take this point half here, then if I draw the line passing through half, then that line will be like this. Okay, assume that it's a straight line. Then you can see that it is touching the graph at 2 points. This is the first point, not the graph, I mean the set is at 2 points, right? That means the vertical line test does not hold for this particular subset of R2, correct? Because I have found a vertical line which touches this set at more than one point, namely one is here and one is here. So I cannot find any function whose graph will be this set. That's not possible for me. Okay, because from here you can see that the value of the function at the point 0 is 1, not function. Suppose there was a function, then value of that function would have been at 0 would have been 1 as well as -1. So 0 would have been mapped to two different points. Okay, and that would have violated the definition of the function. So I cannot find any function, okay, that does not exist, any function f from R to R such that graph of f is equal to s. This is not possible. Okay, so there are sets, in fact subsets of R2 such that they are not represented as graph of any function. Okay, so that will not be possible. But I can modify this set and I can still make it a graph of a function. Okay, so let's do that. If you look at this now, what I have done here is I have taken the same set S but with the extra condition. I am restricting y to be greater than or equal to 0. So y, negative y axis I am not considering. Okay, so this half portion will go. This will disappear because y is greater than or equal to 0. So finally what you will end up with? A semicircle, right? So let me draw that semicircle here. Supposing this is x-axis and this is y-axis. Now we are not considering the negative y-axis because I'm looking at all the points of the form x comma y such that x square plus y square equal to 1. So that's a unit circle with the additional condition that y cannot be negative, right? So this negative half of y won't come. So my function will be from -1 to 1 and it will be a semicircle of this type, right? And it will touch the y-axis at 1 here, and this is the graph, this is the set S. Okay, so that's the set S that's given to us. Yes. Now for this set S, can I is first of all, does there exist a function whose graph will be equal to this set? If you look at the vertical line test now, then you, no matter which vertical line you draw, that will always touch this set at most once. This vertical line is not touching the set, that's okay. At most one meaning what? Maximum once, right? So there will be lines, vertical lines, which are not touching the set, that's okay, but lines which are touching at most once. Okay, exactly once. So from the vertical line test, it's clear that this set will be a graph of some function. Okay, so let me put it down. By vertical line test, S is a graph of some function. S is a graph of some function. So the next question that pops up is, how do you find that function? Okay, so we are interested in finding the function f from R to R in this case, which satisfies these conditions and which will represent this set is. Okay, so we are already given the pair x comma y satisfying this equation with y greater than or equal to 0, right? And now when I find a function, what do I actually look out is the value for y. Y of x, y is nothing but the value of the function, right? So we are actually looking out for y now. So if you transfer this x square on that side, y square will be equal to 1 minus x square. So there are two choices for y now, either root of 1 minus x square or minus of root of 1 minus x square. So y is plus or minus root of 1 minus x square, right? But y cannot be negative because we are given that y is greater than or equal to 0. So this possibility now is ruled out and I will have only the positive square root of this term, right? And this y is nothing but f of x. So f of x is equal to root of 1 minus x square. Now, what is the domain of the function? You cannot say that the domain of the function is full of R, because if you see the point 2 here, 2 has no image, right? 2 has no image. So if you see here, if you look at the x-axis, at -1 it is having an image, okay, that's 0, and all these points, I will put them in red. All these points, if you see, which I'm marking now in red, those points are having images under this function, right? So therefore, if you take f to be a map from -1 to 1 closed, because at -1 and 1 also the function is having some value, right, to R defined by f of x is equal to root of 1 minus x, and this is the function whose graph will be exactly this set which is given to us, capital S, and graphically it looks like this, a semicircle. Okay, now instead of this condition y greater than or equal to 0, one can also look at the condition y less than or equal to 0. That time you will get the second half of the semicircle downwards this way. Clear? So this is how vertical line test works, and if it works, then how do you get the function? This is one demonstration how you obtain the function whose graph will be the given set. Okay, next we have maximum and minimum of two functions. Supposing x is a non-empty set and you have two functions f and g from x to r, then the maximum and the minimum of these two functions f and g, denoted by maximum of f and g this way and minimum of those functions f and g, denoted by this, they are also functions from x to r. Okay, so given two functions from x to r, f and g, the maximum and minimum is also a function from x to r, and maximum of f comma g of x. So this is like a function now. You can give this some name. You can say h, say. Okay, so you can call this as h of x if you wish. So maximum of f and g is a function, and it is defined to be maximum of these 2 points f of x and g of x. Okay, so you can think of that h of x to be this. that will be the maximum of the points f of x and g of x. Okay, so what you do at x, at each point from the domain, you find the value of the function f and the g. Out of these two, you pick up the maximum, right? Because it's a finite set having only two elements, the maximum will definitely exist. One of them will be the maximum. If they are equal, then same value you will get, right? So that's how maximum of two functions is defined. At each point, you look at the maximum of f of x and f of g, and you pick up the maximum, and that is defined to be maximum of these two functions at the point x. In a similar way, you can talk about minimum. So you can call this as something, let's say h1 or some other notation also you can use. You can say phi of x. So minimum of f and g two functions at the point x is minimum of f of x and g of x. Okay, so the smaller value out of these two values, f of x and g of x, will be the minimum of the function f and g at the point x. Okay, so here is an example. Plot the graph of maximum of f and g and minimum of f and g where f of x is equal to x and g of x is equal to minus x, defined on this domain minus 2 comma 2 closed. So let me plot those two functions and we will see how the graph of their maximum looks like. So supposing this is my xy plane and I have the domain that's minus 1 to 2 closed. So let's say this is minus 1, this is minus 2, here I have 1, here I have 2. So my domain is this, which I'm marking as a closed interval. So if you plot the function f, I will mark the function f in red, then it is equal to x, right? So it's of the form y equal to x. So supposing this 2 is here and this side it's more or less here. Okay, so I draw the function f of x is equal to x, more or less, although it's not correct. Okay, you can just assume this 2, you can get this 2 here and you can take this 2 on top there. So this is the function and I can come down also this way. Okay, so supposing my 2 minus 2 is here. So this is the function f of x is equal to x, and if you plot the function f of x is equal to minus x, I will do that in, let's say, green. It will be this way, right? So at each point in the domain, what you do is you look at the maximum. So at 2, you see what is the maximum. Value of the function f is here and value of the function g is here. G of x is equal to minus x. And maximum of this point and this point, you can easily see that it's this. So let me put that in blue. So maximum of all these points here is this now, blue line, which I'm marking, right? Diagram has become very bad. Let me draw that again. So if you compare these values which I've marked in blue and this down values, you can easily see that the blue ones are bigger. And once you cross 0, the maximums are here because they are above the x-axis. So whatever I've marked in blue now, that is the maximum of the functions f and g. That is the graph of this function. Okay, and similarly, you can also talk about the minimum. So at each point, you will be looking at the minimum. So that time you will get the points here below, right? So the minimum will be this half here. I can put that in some color. Let's say yellow. So the graph marked in yellow is the graph of minimum of the two functions f and g. Okay, so this is how, you looking at the graph, you can see how the maximum and the minimum functions of two given functions looks like. All right, so I will stop with this, and in the next lecture I will be talking about one functions. These are my references. Thank you.